Welcome back to another episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
This will be a Q&A episode where you, the listeners, have written in your questions and we will answer them for you. I am your host, Heidi Campo, joining you for possibly my last episode. We don't know quite yet. Andrew might be back next week, but if he's not, then I'll be back and I will say goodbye again. But until then, we still have, for now and the foreseeable future, we have our beloved Professor Fred Watson, astronomer at large. How are you doing, Fred?
Yeah, good to see you again, Heidi, as always. And yes, this could be the longest goodbye ever, couldn't it really? It could go on for weeks.
It's like when you are parting ways with someone, you say goodbye, and then you realize you're walking the same direction.
Yeah, exactly. I know. Yeah, I do that all the time.
And then I never quite know. It's like, well, do I keep talking to them? Do I say goodbye again? Do I pretend they're not there? I usually end up commentating and narrating the whole thing to make it more awkward. Well, anyways, let's just jump into our questions because you guys have some really fantastic questions as always, which we appreciate. Our first question of the evening is a written question from John Kerr. And John says, "Hey, Space Nutters, this dilemma is driving me nuts. If the moon's gravitational pull has such an effect on our ocean's tides, for example, a 30 centimeter rise in tidal waters twice a day, that's a lift of 300 kilograms worth of water per meter square, why doesn't the moon's gravity affect us as drastically as the oceans? I will sleep better once resolved. With thanks." Oh, so I have so much. I feel like I could say about this one too. But please go, Fred.
Well, you might give a better answer than me, Heidi. So yes, well, it does. The moon's gravity does affect us as drastically as the oceans because we go up and down with the oceans. In fact, the land itself goes up and down slightly. If I remember, it's about a foot or something. Oceans sometimes go much more than that. That 30 centimeter that John mentions. Sometimes it's many meters. So what's happening here? It's the critical feature of tides is that they are caused because of the difference in the gravitational pull of a body like the moon. And let's just think about the moon and the Earth. It's a difference between the moon's pull on one side of the Earth and the other side of the Earth. So tides are all about the difference in the gravitational pull of an object across the diameter of another object, a big object, and that's the Earth. And so the reason why our bodies don't stretch and shrink is that we're only a couple of meters tall. Actually, my son's 2 meters tall, but that's quite tall. All right, 1.5 meters tall. But we're certainly not tens of thousands of kilometers, which is what you need for the gravitational effect to be noticeable, as it is with the ocean tides. So we don't get stretched and shrunk. We would if we were near a black hole. That's the principle of spaghettification. It's when your feet feel a higher gravitational pull than your head and you get turned into spaghetti. That's a tidal effect, an extreme tidal effect, but you need something very peculiar like a black hole to notice that. So for an object like the moon, we simply just go up and down with the oceans. If we're on the ocean, we go up and down with the land if we're on the land, but we don't get stretched and shrunk because we're too small. I hope I hope you sleep better after that.
Well, maybe I'll scare him because I was going to say, but it does affect us a little bit. Not like the oceans at all, but the human body is roughly 60% water and every cell in our body is roughly 70 to 80% water. Now, what I'm about to say next is not something I'm looking at a science review for. It's more anecdotal, but nurses will often say that there is way more emergency room activity on a full moon. Police officers will say that people are crazier on a full moon. And there's a lot of lore around women's cycles aligning with moon cycles. More women go into labor and give birth around the moon cycles. And historically, there is a lot of, stories about personality around moons. You think of werewolf stories. So humans we are affected by the moon to some degree. And that would be a interesting, probably further research. And I'm sure there's whole departments dedicated to the psychobiological effects of humans and the moon. But it is interesting. So no, we're not affected like the oceans, but there is something to that.
Absolutely, yeah. And you're quite right. There's natural cycles that align with the moon. And it's not just humans as well, with things like coral spawning. That's very much tied to lunar phases. And some of that's not very well understood. But I think the thrust of John's question is why aren't we being stretched and shrunk like the oceans are? Perhaps I've got it wrong, but anyway, that's the answer. And I agree with you too, Heidi.
Let's take a moment to talk about our sponsor, Insta360 Go Ultra, a pocket-sized camera that's redefining how you capture life's adventures. Imagine a camera no bigger than an Oreo, weighing just 53 grams, yet packed with the power to shoot buttery smooth 4K video at 60 frames per second. What makes the Go Ultra stand out? Its magnetic mounting system lets you get creative with your shots in seconds. Clip it to your shirt or hat for hands-free point-of-view footage while you're running, biking, or chasing your kids around the park. Or stick it to any magnetic surface, think bike frames, gym equipment, or even a street sign, for unique angles that no other camera can match. The Go Ultra's upgraded sensor and AI chip ensure your shots are crisp and vibrant, day or night. For stills, it delivers 50 megapixel photos packed with detail, perfect for everything from family snapshots to viral-worthy posts. Here's the best part. For the first 30 Space Nuts listeners who purchase the Insta360 Go Ultra at store.insta360.com, you'll score a free sticky tabs accessory to mount your camera on anything from backpacks to winter jackets. Just use the promo code SPACENUTS at checkout. That's store.insta360.com, promo code SPACENUTS. Check the description for links and more details. Don't miss out on this tiny titan of a camera that's ready to capture your world like never before. Now, back to the show.
0G, and I feel fine.
Space Nuts.
Our next question is an audio question from Ben. With our audio questions, we like to queue those up so you, the listeners, can hear their question as well. I'm just going to give Fred a second to get his question ready as well. And we are going to play Ben's question for you now.
Hey guys, it is Ben, an American living in Mexico. Thanks for answering my last question about how observatories interrupt their observing schedules to deal with transient events. And I've just got a follow-up question. Are there any scheduled observing things that might be immune to these sorts of interruptions? I know sometimes there are time-sensitive observations of like transits or something that astronomers use to determine shapes of objects and stuff like that need to occur at a specific time. So I was thinking maybe those or something that wouldn't be interrupted. But yeah, that's my question. Thanks. Loving the show. Bye.
That's a great question from Ben. And Ben's absolutely right. And he's actually highlighted at least one of the reasons why you wouldn't interrupt observations. So his original question was about what we might call target of opportunity observations, where an observer on the telescope would stand aside if there was something like a supernova explosion that needed the same instrument to observe it, to give us something that was only going to last for a very short time. And that happens a lot. Perhaps the best known of those was back in 1987, which I remember very well, when that was the last time a naked eye supernova went off in our skies. Down here in the southern hemisphere, it was in the Large Magellanic Cloud, our nearest large dwarf galaxy. It was visible to the unaided eye, first for 400 years. And of course, our telescope was only 10 years old then. It was state of the art, and pretty well everything was pushed off for observations of this object. But it is usually, it's not usually an event where there will be a conflict between the scheduled observer and the person who was requiring the target of opportunity observations. It's usually that the scheduled observer would have had an understanding at the outset that they might need to stand by and let somebody else take over the telescope for the purpose of whatever their observations are. However, Ben's absolutely right. There are some observations which are scheduled, which themselves are time critical. And so you would rule out the telescope being taken over for those events. One I was involved with, because I was astronomer in charge of the telescope at the time, and this is probably 10 years ago, there was an occultation of Pluto. So what that means is, actually, it was an occultation of a star by Pluto. What that means is Pluto passed in front of a distant star, and we could observe the brightness of the star. And what we wanted to do was look at the way the star's light diminished as it passed through Pluto's atmosphere. This actually, it was before New Horizons flew by Pluto in 2015. So we didn't really know much about Pluto's atmosphere. It's very thin, very tenuous. But the observations that were made actually allowed us to form details of it, in particular that it's quite layered. It's not a smoothly changing distribution. So that was very much a time-critical observation. And you would not get, even if there'd been a bright supernova in the sky that night, it probably would not have taken over the telescope. I think it would have, the occultation by Pluto would have been the thing. And as exactly as Ben says, there's occultations are when an object passes in front of a star, usually, or another object. But it's a way of allowing us to work out the shapes of asteroids and things of that sort if they pass in front of a star. So that's the really quite important observations, and very much time critical in themselves. So you wouldn't want them to be taken over by others. But it was a great question.
It was a really interesting one. Yeah, it kind of gives us the inner workings of astronomy. Our next question, I'm actually going to read two questions because they are similar, but we want to get both questions' perspectives. So the first one we're going to read is from David. And David says, "Hello, Heidi and Fred. My question is regarding meteor showers and why we keep seeing them annually. If meteor showers such as Perseus occur when the Earth passes through the debris left behind by comets as they orbit the sun, what prevents the Earth from clearing the debris from our orbital path after the first pass, leaving our orbit free of debris until the next comet comes past? Cheers, Dave." And then we have Brian with his question, which is similar. And then Brian says, "Can you explain the orbital dynamics associated with annual meteor showers? We orbit the sun, but the whole solar system is rotating around the Milky Way, which itself is moving. So is the comet trail in a static stripe of debris, which we bisect on the same point in our orbit each year, or is it in the orbit of the sun or galactic center or other? If it's in our solar orbit, why do we catch up with it? And why don't we effectively leave a hole in the debris, diminishing the meteors every year? From the dark stars, North Yorkshire, Moons National Park."
Yeah, the national, it's North Yorkshire Moors National Park. It's a place I know well, in fact, in the north of England, and they do have dark stars. This is from Brian there. I wonder whether Brian knows my friend Paul Cass, who also works at the North Yorkshire Moors Dark Sky Park. Anyway, that's a different aspect of all this, Heidi. And I might mention that Dave, who had the other question, was from Inverell here in New South Wales. So a question from the UK and a question from Australia, both effectively asking the same thing, which I thought was worthwhile bringing these two people together. So yes, the bottom line is, and you've got to sort of think of it in 3 dimensions, it is to do with the orbits of comets. A comet moves in usually a very elongated orbit, and the sun is one end of it. It passes close to the sun and then disappears into the depths of the solar system. And when it gets near the sun, the comet starts basically ejecting dust, and that dust trail remains within the comet's orbit. And so those dust particles are sort of moving with the comet. They're moving in the orbit as well, but they smear out because they've got their own motion. And so essentially a comet leaves a trail of dust exactly in its orbit. And if that orbit intersects the Earth's orbit, then the Earth will pass through the trail of dust. And that's exactly what it does. And when that happens, that's when we get a meteor shower. But the reason why, it doesn't soak up all the dust as it goes through is because that dust itself is moving. And it's not just a single dust cloud that you're punching a hole in. The dust is a stream of stuff that's moving through space with the same velocity, more or less, as the comet had. And so what you've got is a region of space that's rich in dust, but it's being replenished by the motion of the particles. So yes, the Earth plows through it. It doesn't really make a hole in it because we only sweep up 12,000 kilometers diameter worth of it, because that's the Earth's diameter. And the dust stream might be many tens of thousands and perhaps even millions of kilometers wide. Maybe not millions, but certainly tens, hundreds of thousands possibly. So you've got a wide trail of dust that is a reservoir for the Earth to sweep up and see the meteor showers. So it's constantly being replenished. That's the bottom line. And hopefully that's the answer to both those gentlemen's questions.
Oh, that is fantastic, Fred.
Okay, we checked all 4 systems and skiing with a go.
Space Nuts.
I'm getting sad. I'm going to do my last question now, unless I'm back next week. We will see. So backstory for those of you who might be new listeners, our regular host, Andrew, he's been on a cruise around the world and he's back now, but he has quite the conundrum getting settled back in. We'll let him tell you all that story, and him and Fred get caught up when he is back, but he's had quite an exciting time. All right, so our last question is an audio question from Lou.
Hello, Heidi and Fred. My name is Noah from Manchester, England. I'm asking a question about the Goldilocks Zone. The Goldilocks Zone is only habitable for life on Earth. For extraterrestrials, however, they might need to exist at the very edge of the solar system or at the very centre of it. Is the Goldilocks Zone nearly compatible for all life in the universe? Love the podcast. Hope you keep making more.
Lovely question from Lou. Manchester, again, a place I know well. I grew up not very far from Manchester in the north of England, so this has been a bit of a nostalgia segment for me. But a great question. Is the Goldilocks Zone applicable to all extraterrestrial life? And I think the answer is no, because when we talk about the Goldilocks Zone, it's that region surrounding a star where the temperature is not too hot and it's not too cold, but it's just right for life to exist. It's why it's called the Goldilocks Zone. I've got a feeling it was a colleague of mine who coined that expression as well a long, long time ago. It relies on the fact that we are beings. In fact, all life on Earth is based on water. We use water as our working fluid. As you mentioned in our question on tides, Heidi, most of our bodies are made of water. And that the same is true of most living organisms. Water is a large part of it. And so liquid water is, for us, the perhaps the strongest feature that might be used as as an indicator of where life might form. If you've got water, maybe you will have life. That's always been the mantra. Follow the water. So the Goldilocks zone is where you could put a planet and it would be capable of having liquid water on its surface, not frozen, not vapor, but liquid, which is what we need. So it's very specific, is the Goldilocks zone, to life forms that are like ourselves, that are based on water. And well, maybe if there is life anywhere else in the universe, it will be based on water, but there are other possibilities as well. And people have wondered whether perhaps the seas and lakes of Titan, one of Saturn's moons, which are made of liquid ethane and methane, whether they might have living creatures in them that rely on those supercooled liquids as their working fluid. We don't know. We've not seen any evidence of that, but it is possible. And so if that was the case, then you'd be looking at an entirely different type of Goldilocks zone. If liquid natural gas was what you needed for these creatures, then your Goldilocks zone will be a very different one from the one that we have. It will be much further from your parent star. So Goldilocks zones are not universal. They're not common to all species, because we don't know enough about what other species might be like. But it's a good start. That's why we look at the Goldilocks zone with interest, because the only life forms that we know use water, and the Goldilocks zone is where water might exist. So that's why we look there.
Fred, have you ever seen that TV show? I think it's on Netflix or Amazon, called Alien Worlds, where they break down scientifically the conditions that would be needed for different life on different planets. And then they hypothetically come up with a planet that's a certain way. Have you seen it?
I haven't, but it sounds like one that I ought to see. Yes.
It's very interesting, and that might be one to lose interest in, because they come up with 4 hypothetical planets. One of them's a jungle, one of them's a desert, one of them is the atmosphere is so dense that it's almost like water. So there's all these animals that look marine-like, but they are like birds. And it's very cool just to play around, because they use real physics and then talk about the hypothetics. It's kind of fun. And then I won't tell you about the last planet, because it's kind of it's a fun surprise. It's a fun surprise planet. It's not Earth. It's not Earth. It's a very interesting hypothetical planet. But I do recommend that show.
Sounds great. I'll check it out. Thanks, Heidi.
Yeah, it's a good one. Well, I guess that's it for our Q&A episode. So I just want to say, if this is my last episode, that it has been an absolute pleasure and delight being on here. Thank you all for your wonderful and kind questions. Fred, thank you for having me. If you all want to stay in touch, you can follow me on LinkedIn. It's just my name, Heidi Campo, which is CAMPO. And then I think it's on there is CSCS, which is one of my certifications. That would be Comet Sun, if we're spelling it phonetically. Comet Sun. So Heidi Campo, CSCS, if you want to follow me on LinkedIn. I'm also on Instagram, but it's mostly just pictures of my dog and me talking about fitness stuff, which may not be everybody's cup of tea. Fred, it has been a delight. Thank you.
Oh, it's been a delight for me too, Heidi. And I hope we do this again sometime. It might be next week, but it might be next week.
It might be next week. Yeah, we'll be in touch, and I'm always here if you need me. Till then, we'll catch you all next time.
Take care.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.